All right, we're rolling.
Is it working? Okay, here, let me. All right. So, we're going to finally start Fourier series. The homework, we'll just say it's the first 14 problems, not the first, not 3 through 16 or 1 through 16. Next, the Fourier series are simpler when you think in terms of complex Fourier series. At least that's the way I think of it. And the reason is that we've got these phases, e to the I and x over square root of 2 pi. These functions are orthonormal on the interval 0 to 2 pi. And what I mean by that, of course, is integral 0 to 2 pi e to the IMX over root 2 pi complex conjugate times, well, we don't really need a parenthesis there. E to the I nx over the square root of 2 pi dx. That this, of course, is simply the integral from 0 to 2 pi e to the I n minus m x over 2 pi dx. And now this integral is a little bit tricky. If n and m are different, first of all, n and m are integers. Not just real numbers or rational numbers, but integers. If n and m are two different integers, then you can do the integral immediately, and what you get is e to the I n minus m x divided by 2 pi I n minus m evaluated between 0 and 2 pi. This is for n not equal to m. And you see that the exponential is 1 when x is 0, but when x is equal to 2 pi, it's 2 pi times some integer that's not 0, and e to the 2 pi n I is 1, so the exponential is 1 at both limits, and so when you subtract you get 0 if n is not equal to m. On the other hand, if n is equal to m, then this is a very simple integral. It's 0 to 2 pi, integral 1 over 2 pi dx. And of course, this is the calculus problem that you always wanted on your final exam. And this is just 1. So the answer is that this integral here is delta nm. The Kronecker delta. 1 when n is equal to m, 0 otherwise. So that's the orthonormality that's at the basis of Fourier series. It's also at the basis of, this is essentially, in the linear algebra, we learned if we had an orthonormal basis, we could expand things in a very nice way. That's what Fourier series do for us. My understanding, I'm not in any sense an expert on history, but when Fourier was doing this about 200 years ago, his papers were initially greeted with a great deal of skepticism, but in fact what he was doing was making a huge contribution to mathematical physics. He was actually I think he was trying to study heat, and the Fourier series was something he introduced in order to study the diffusion of heat. Okay, anyway, so what you can do with these orthonormal functions, just as you can with orthonormal vectors, you can expand them you can expand an arbitrary function in terms of them. So the expansion looks like this: f sub n e to the I n x over square root of 2 pi. And if you want to skip ahead, I described the analogy with linear algebra and bases in a later section. I don't know, section 2.9, 2.10. Okay, now to find out what these coefficients are, well, a good guess is to write 0 to 2 pi e to the minus I n x square root of 2 pi f of x dx. So this thing is like, it's kind of like that, right? And so now what we're doing here is I should say x, that is to say it's some fn xn, where xn is e to the I n x over square root of 2 pi. So I'm doing the analogy now with linear algebra. And now to find out what the fn's are, well, what we do is take the inner product here with that is to say fn. In other words, if we write the identity operator as a sum of nn as usual, then we can think of this as f looks like that, and so xf is a sum x n and f and well, anyway, the formula for this fn, it comes out this way, because if we put in this integration, we have e to the minus I n x over square root of 2 pi. And then we have a sum, let us say fm e to the I m x over square root of 2 pi dx. And now we use the orthonormality of the basis functions, namely that they're orthonormal on this interval. And so this then is integral 0 to, well, the integration is done, so it's simply a sum on m of f sub m delta nm, which is f sub n. So in other words, f sub n is that integral. And looking at it now from the other point of view, it's nx xf and integrated dx over yeah, I guess I would just say integrated over dx, and the idea is integral x dx. Let's see, if I want, that will have a square root of 2 pi, that'll have a square root of 2 pi, so this in fact is the identity. So the identity is an integral 0 to 2 pi dx is the identity, and then when we take the inner product, each of these guys gives us a 1 over 2 pi. And we can say xf is f of x over square root of 2 pi.
All right, anyway, wherever, by the way, the issue of where to put the 2 pi's is really arbitrary. You just have to have the right number of them. And so when we look here, we see that the orthonormality relation is dx over 2 pi. The integral of the 2 phase factors gives you the Kronecker delta. So you need 1 over 2 pi somewhere. Now, this is then the Fourier series. So maybe I can use a colored chalk here. This is the Fourier series for the function, and the coefficients Fn are given by these integrals. So those 2 equations summarize the essence of Fourier series. So in a certain sense, this is almost the whole story in a nutshell, and the rest of the chapter is details. But the details are important, and so you shouldn't just use the rest of the chapter as kindling. All right. Okay. Now, an important thing to mention at the outset is these functions, e to the I n x, are periodic functions, and that's why we had this orthonormality relation. It was the fact that these phase factors are the same. E to the I n x is the same at x equals 0 as at x equals 2 pi. If we write the function f of x, any function f of x, in this form, the right-hand side is periodic. So this thing here is periodic. On the other hand, we might start with a function f that is not periodic. So then this equation can't be really exactly true. It's instead something that will be very good, except at the endpoints and outside the interval.
Can I ask you, why did you sum the Fourier series? Why are we going from minus infinity to infinity and not 0 to infinity?
Well, because our basis functions are e to the I n x for arbitrary n, integer, minus 57, plus 43, whatever. Good question. Okay, so now let's look at some of the details. Some of the details are, for example, what about the complex conjugate function? Well, f star of x would then be a sum f star n e to the minus I n x over root 2 pi. And if we change n to minus n, we can say this is a sum f minus n star e to the I n x over root 2 pi. So what we can say is that the coefficients f sub n of the function f star are the coefficients f sub minus n of the function f complex conjugated. Or to write it more simply, f sub n, well, I guess maybe I should write it this way rather than trying to write it in a simpler way. But if the function is real, then f star and f are the same. So if f star equals f, in other words, the function is real, then f sub n is equal to f sub minus n star. This is a little bit like the hermeticity of a matrix. And remember, with a matrix, you have real eigenvalues. A simple example of a Fourier series, this is sort of an instantaneous Fourier series, is this rather elaborate one. E to the, so suppose this is the function, f of x is the exponential of e to the ix. Well, we know what the formula for an exponential is. It's just the sum, n equals 0 to infinity, of e to the ix to the n over n factorial. So this is the sum, n equals 0 to infinity, of 1 over n factorial e to the inx. So this is a strange Fourier series. It has no negative terms, so it's the thing that you were asking about. Here's a Fourier series with only positive integers, very simple coefficients, and in fact the coefficients are, I mean, these are the, you couldn't ask for nicer coefficients because this makes this thing, makes this series converge just incredibly fast. All right. Another example is shown in figure 2.1, beats. And if we write f of x as the sum of two sines, sine omega 1x plus sine omega 2x, with similar frequencies, omega 1 approximately equal to omega 2, then what you can do is you can rewrite this as 2 cosine a half omega 1 minus omega 2x times the sine of omega 1 plus omega 2 over 2x. And what you've got then is, this is a very slow, if omega 1 and omega 2 are approximately the same, this is a very slow frequency, and this can be a very fast frequency. So what I did was in the figure, I've got omega 1 equal to 30 and omega 2 equal to 32. And this you can hear in singing. If you have two people who can, you have two singers who sing with almost this, they both try to hit the same note. You can hear some beating. And I always found that beating to be disagreeable. Apparently some people think it's a feature.
That's why you're better off having people sing harmony than trying to lock on to
Oh, so you mean the two people are not singing the same note, but one is a, what, twice the other frequency, for example?
Well, the ratio of notes in a major chord of 4, 5, 6.
Say it again?
Ratio of notes in a major chord of 4, 5, 6.
4, 5, 6?
Yeah. So just...
So omega and then 5/4 and then 6/4 omega?
Yeah. I'm 4.
All right, anyway, this isn't a music class, so I think I'll just stop there. All right, any more questions? All right. So these are the basic ideas. Now some details. One detail is over here, I chose the original interval to be 0 to 2 pi. All these intervals were 0 to 2 pi. Well, suppose the function f of x is periodic with period 2 pi. Okay, so maybe turn the thing around this way a little bit. Suppose f of x is periodic with period 2 pi. Then these functions, the coefficients f sub n are going to be independent of what 2 pi interval we choose. In other words, we could also call this r to 2 pi plus r e to the minus I n x f of x square root of 2 pi dx. So it's the same thing. So if f of x plus 2 pi n is equal to f of x, then these two things are equal. So you can choose any interval of length 2 pi if the original function is periodic. On the other hand, if the original function is not periodic, then the coefficients will depend upon what interval you choose, and whatever interval you choose, you'll get a good representation for the function inside that interval, but not outside it, if the function is not periodic. Okay, the other question is these 2 pi's. Here, we've got square root of 2 pi, square root of 2 pi, over here, square root of 2 pi, square root of 2 pi, square root of 2 pi. It gets tedious after a while to write square root of 2 pi. And so, sometimes people do this. They write f of x equals sum, just dn, e to the I n x, and then dn is 1 over 2 pi, integral 0 to 2 pi, dx, e to the minus I n x, f of x. So I'm using d to say that I put the 2 pi's there, but I don't.
So if it's just a periodic interval 0 to L, would it just be 1 over L there instead of 1 over 2?
Right. There's a 1 over L. Absolutely. That's coming up I'll be getting to that in maybe 10 to 15 minutes. Another choice is f of x equal 1 over 2 pi, sum Cn e to the I n x, and then Cn is equal to integral, and here, for a change, I change the interval. Cn is f of x e to the minus I n x dx. So we could do the series with the 1 over 2 pi there, and then the Cn's don't have a square root of 2 pi. And here I took a 2 pi integral from minus pi to pi. Okay. All right, now for some examples. There were lots of examples. There were some typos in the labels of some of the figures, and I added new typos to the web page of typos and errata and clarifications. So the first example is a function e to the minus m absolute value of x, and here I'm thinking m greater than 0. And since this is a symmetric function about 0, it's natural to do the Fourier series on an interval from minus pi to pi. And so the dn coefficients might be minus pi to pi, dx over 2 pi, e to the minus I n x, e to the minus m absolute value of x. Notice here, because the original function was an exponential, it makes sense to use complex exponentials rather than sines and cosines. And we can split this integral into 2 pieces. There's integral minus pi to 0, dx over 2 pi, e, and the reason why I'm doing that is that the absolute value of x, of course, we can write it simply if we have x, distinguish between x negative and x positive. So on the negative interval, this is m minus I n x plus integral 0 to pi dx over 2 pi e to the minus m plus I n x. And so we do the integrals and we find what we get is 1 over pi m over m squared plus n squared 1 minus 1 to the n e to the minus pi m. So that's our expression for dn. And in this case, we see that it goes down as 1 over n squared. We'll see that this is a general rule, at least for functions that have nice properties. This original function is continuous, and it's also differentiable except at 0. So it's piecewise continuous. And okay, so let me go on a little bit further. The actual series is e to the minus m absolute value of x, and if I skip a line here, this is 1 minus e to the minus pi m over m pi plus a sum n equals 1 to infinity. So I'm combining these things with negative n with positive n, and so what we get is 2 over pi m over m squared plus n squared, and then 1 minus 1 to the n e to the minus pi m, and then cosine nx. So you can see two things happening. If you've read ahead, you can see that since this function starts out real, it kind of turns into a function, something involving sines and cosines eventually. Secondly, since I took m to be real, in fact positive, and so this rule over here, well, since m is real, d sub n and d sub n star are the same. So the d sub n's are real. And also, since the function is real, d sub n is d sub minus n star, which is d sub minus n. And so this is a function that's even in n, and it's obviously even here, but it's also even here. Minus 1 to the 2, or minus 1 to the 3, say, is the same as minus 1 to the minus 3, and both are minus 1. So what's plotted in figure 2.2 is the function itself is solid, and in dashes is simply the 10-term series. The 100-term series was so close to the 10-term series and so close to the function that I just couldn't make it visible by putting it in. Okay. Now, here I was using Fn for using square root of 2 pi twice, and d's for putting the 2 pi there, c's for putting the 2 pi there. I'm not going to use a special notation according to where the 2 pi's go. I'm just going to put the 2 pi's wherever I feel like. That's what I encourage you to do, but what you've got to make sure about is you adhere to one convention while doing, until you finish each problem. You can switch conventions between problems, but not during problems. Otherwise,
what does the spectrum analyzer do?
What?
What does the spectrum analyzer do?
Spectrum analyzer?
Yeah, I get the Fourier components, right? But does it?
You're talking about a piece of equipment?
Yeah. Does it?
Well, I mean, it would, I guess, be something that would kind of do a Fourier transform of the thing, and.
I mean, does it worry about the 1 over 2 pi, square root of 2 pi?
I mean, it takes it into account one way and the other, and. let's leave that aside for the moment. Okay, now we're going to go to the case where the functions are real. So we've got now f of x star is f of x. So f is real. And now, what do we have? We have this situation here that d sub minus n is equal to d sub n star. And in particular, that means that d0 equals d0 star, so d0 is real. The other ones aren't necessarily real. They satisfy, you just have to satisfy that relation. But when we put them together and get our function f of x, what we get is d0 plus a sum from 1 to infinity dn e to the I n x. So I'm leaving out the two pi's in the expansion, and they'll occur in the inverse formulas. And then we'll have a sum n equals minus infinity to minus 1, because we did d0 over here, n equals 0 over there. And this would be dn e to the I n x. And now, we can rewrite that as d0 plus the sum from 1 to infinity of dn e to the I n x, and then these guys would be d sub minus n e to the minus I n x. So if we flip n to minus n, this series can be combined with that one in this way. On the other hand, d sub minus n is d sub n star. And so this is equal to d0 plus the sum from 1 to infinity of dn e to the I n x plus dn star e to the minus I n x. And now we can, of course, expand e to the I n x is cosine nx plus I sine nx. And this is then d0 plus the sum n equals 1 to infinity dn cos nx plus I sine nx plus dn star cos nx minus I sine nx. Now, if we combine the cosine terms and the sine terms, what we get is d0 plus the sum n equals 1 to infinity dn plus dn star cos nx plus I dn minus dn star sine nx. Now, of course, dn plus dn star is real, and dn minus dn star is imaginary, but when you multiply by I, you again get a real number. And so, if we set a sub n equal to dn plus dn star, and b sub n equal to I dn minus dn star, and we can write dn as a half an minus I bn. In other words, you just you use these two definitions and you can recover that expression. Okay, so when we do that, this Fourier series becomes a 0 over 2 plus a sum n equals 1 to infinity, an cos nx plus bn sine nx. Okay, so you might say, well, why is there a 2 here? Well, it's that let's see, D0, we've got D0 and A0. You see A0 here is D0 plus D0 star. But on the other hand, that's just 2D0. So the original term here was D0. D0 is A0 over 2, and that's why it's A0 over 2. All right, so this is the way people normally introduce Fourier series. They say, let f of x be A0 over 2 plus this sum of sines and cosines. But I think this is much more complicated. I think the exponential thing is easier to understand, and it makes better contact with linear algebra and so forth. On the other hand, when you're doing Fourier series for real functions, it makes sense to do this. And if you choose if you have a nice function that's even or odd on some interval, and you get to choose your interval, you can arrange very often to have all the cosine terms vanish or all the sine terms vanish. These, of course, are in academic examples. If you're in real life and you're given some function in some interval, then you're stuck. And if the function's complex, use the complex. If it's real, use the sines and cosines. Yes?
So if we do it in the complex, do we just take the real and the imaginary parts? If we do the whole Fourier series in complex notation, then we want to get an and bn, then we just get the complex in the real part of the...
Well, you can just, you can, I mean, if you want, you can do everything in complex notation and then just do the translation that I went through at the end.
Okay.
Sure. Whether that's easier or not depends on the problem. Sometimes it'll be easier, sometimes it won't.
So I think my other question is, if we have some other function, like cosine x, which you can always think of as the real part of e to the ix, is it, like, does it work to first take the Fourier series of e to the ix and then do something to get the Fourier series of cosine? Is there a trick to doing that?
I don't know. I have not actually followed in detail everything you said. I would say, with each problem, think, and you'll see different ways of doing it, and then you can just estimate which is easier.
Okay.
And if instead you do it the hard way, well, you'll learn not to do that in the future.
So are you basically just saying do everything in the complex plane and then just take the real part at the end of it?
He's saying that. I'm not
Is
saying
that what you're saying?
I'm saying, yes.
That's what you're saying?
Yes.
And that should be fine, right?
Yeah, it works. It works. There's no doubt about it. You can certainly do that. Or you can,
So this is to say that the Fourier series for a real function, f of x, the Fourier coefficients aren't necessarily real, right? That's what you said here.
if the function is, okay, let's think about it. Great question. If the function is real, what are these an or bn? Well, let's look at them. An is real, and bn is real also. So the coefficients are real in this structure here. On the other hand, we started here with a function that was real. We started with the real function and derived this series. This series only works for the real functions, We derived it for real functions. So if your function is complex, do the complex representation. If your function is real, you have a choice. You can do complex or real. All right. But now we need to say, well, what are the rules for Bn and An and A0? Well, in a sense, you can just compute them from the rules that you already know for Bn and so forth.
in particular, an is dn plus dn star, so this is integral 0 to 2 pi e to the minus in x f of x plus e to the I n x f star of x dx over 2 pi. So this is dn plus dn star. Right. But now f is real, so we can get rid of this. And then what we have, combining the two, is we can say this is integral 0 to 2 pi, and I think I see a typo here. This is e to the I n x plus e to the minus I n x over 2 dx over pi, and so this is integral 0 to 2 pi cosine nx dx over pi. And yeah, I see a typo on the right-hand side of 211 as an extra factor of 2. So an is given by this expression. What about bn? Well, bn is I dn minus dn star. And so this is integral 0 to 2 pi I e to the minus I n x. F, of course, is real, so we can say minus e to the I n x f of x. F of x is real. Dx over pi, and we put the 2 here. When we bring the I down, we bring in a minus sign, and so this is equal to integral sine nx dx over pi. And, okay, wait a second. You guys should have shouted at me. I left out the f of x. And I left it out here also. My goodness. Okay, so we have f of x here, also there. And here we have an f of x, so we have f of x here. So these are the bn coefficients. So the bn's are like that, and the an's are like this. So if f is a real function, it is probably simpler to do the sine and cosine integrals. If f is a periodic function, you can choose the interval. You can use any old interval of length 2 pi. And consequently, let us suppose that f is an even function. Then I would recommend choosing the interval minus pi to pi, because then f will be even, the sign will be odd, all the b's will vanish. On the other hand, if f is an odd function, also choose the interval minus pi to pi, because then the cosine is even, the function's odd, these a's will all vanish. So if your function is even or odd and periodic, then you're better off with an interval minus pi to pi, because you're going to get half of them to vanish. That means you only have half as many integrals to do. Or in practical purposes, you have one integral instead of 2. Okay. So as I say, in equations 24 to 26, there are certain relations that are satisfied by the sines and cosines. These are sort of orthogonal relations. In other words, 0 to 2 pi sine nx sine mx
dx, and this is equal to pi for n equals n. Not equal to 0, otherwise 0. Well, just otherwise. So I'll put in else. If instead we have 0 to pi cosine nx cosine mx dx, then it's more complicated. It's pi for n equals m not equal to 0, 2 pi for n equals m equals 0, 0, again, otherwise. And then finally, an integral of a sine with an integral of cosine, always 0. So, integral 0 to 2 pi cosine nx sine mx dx, 0 always. Okay, and the reason why we have to toss out the case n equals m equals 0 is that then we would have the integral of sine of 0, which is 0, times sine of 0, which is 0, and you just simply get 0. Thanks, I hope you're okay there. All right, so once again, if the function is not periodic, then the Fourier series will be periodic. The Fourier series will be sensitive to the integral that you choose from r to 2 pi plus r, and the series will differ from the function near the ends of the interval and outside the interval. And I'll show some examples of that in what follows. Okay, let's look at the Fourier series for the function, say f of x equals x squared, something really simple. All right, well, obviously this is even, and so in order to do the, we might as well do the integral minus pi to pi, and because then all this f of x is even, the signs are odd, so on an integral minus pi to pi, all the b's vanish. The an's then are given by minus pi to pi cosine nx f of x dx over pi, and this is integral minus pi to pi x squared cos nx dx over pi. And now, if we integrate by parts twice, now, if you find integration by parts confusing, don't feel bad, I do too. Well, once I had a student who had been taught integration by parts in a really effective way, and it was a woman, and she had some lightning formula for integrating n times by parts. It was rather cute. I always just do it from scratch every time. Anyway, if we do, I don't think I should belabor the integration by parts. Let me just say what we get. In the first case, integrating once by parts, we get minus 2 over n, integral from minus pi to pi, x sine nx dx over pi. And then when we integrate them, and the surface terms in this case vanish because they involve sines. The next time when we integrate this by parts, it's the surface terms that survive, and so we have 2x cosine nx over pi n squared evaluated minus pi to pi, and this gives us minus 1 to the n times 4 over n squared. A0, on the other hand, is What is our formula for A0? I don't actually remember it here.
It's just integration of x from minus pi.
Yeah, it's just integral from minus pi to pi of the function over time. And so this is simply integral from minus pi to pi, x squared dx over pi, and this is 2 pi squared over 3. So altogether, what we have is that x squared is the series pi squared over 3 plus 4, sum n equals 1 to infinity, minus 1 to the n, cosine nx over n squared. All right, so that's our series, and if you look at it in figure 2.3, which is just the integral from minus 1 to 1, you see that a series of 7 terms is pretty good. A series of 20 terms is really great. So 7, okay, 20, really fine, on the interval from minus 1 to 1. On the other hand, as you get near minus pi and pi, you get problems. And in fact, the actual function is this, and what happens is if we are at pi, and let us say minus pi, what happens is that the series is okay, but then it starts to get jittery here. And it's typically off by something like 9%. But then what it does is it's periodic, so it goes back down. In fact, it retraces the thing and then gets jittery and then retraces. And the same thing here. Jittery and then back down, jittery, back down. So the Fourier series is strictly periodic, and the representation is good if you're, instead of minus pi, it's good, say, from minus 3 to plus 3. And it gets a little shaky as you get close to pi and minus pi. This discontinuity is called the Gibbs overshoot. Gibbs was a professor at Yale, and at the time, he was probably the leading physicist in the United States. And Yale, as it often has, it's often treated people badly. Yale's a terrible place. If you avoid Yale, avoid Yale. Yeah.
Your integral of x squared dx over... Oh, never mind. I'm an idiot. I'm sorry. Go ahead.
You're not an idiot. You're very smart.
Oh, no. Stupid mistake. Go ahead. Go ahead. Sorry. I didn't realize... I thought you didn't cube the pi, and then I realized you had a pi in the denominator. That's all I was going to say. And I didn't realize it until I started talking.
Do you want me to have that overshoot?
All right, hold on. Let me come back and give you guys some candy and...
My
Yeah.
question,
No, it's fair. You raise your hand, you get a candy.
if you are trying to find what the Fourier series is from minus pi to pi, are there some special cases if you have to consider what happens at pi? Because something weird happens. Like if you're trying to find it from
Right, if you're doing the series, from minus pi to pi,
yeah,
and the function is not periodic,
okay.
it goes nuts at minus pi and pi. No matter what you do, no matter how many series you have.
So when we have to write
If
down,
the function's not periodic.
okay. So when we have to write down, one of our questions, what is the function? Do we have to do some special things at minus pi or pi, or do we just write down the series and
Well, you write down whatever the series is. You can't, the mathematics, the Fourier series is the Fourier series. It is strictly periodic, the function isn't, so you get a screw up at minus pi and pi. And you get a heavy duty screw up outside the interval.
Is that 9% number, is that rooted in any mathematics, or is that just what it happens to be?
I tell you, I just did a number of examples and calculated what estimated the error, and it always came out to be about 9%. Now, I imagine if you read Gibbs's original paper, he'll prove that it's 9% in a wide variety of cases. But
It has to do with the relative rate of convergence of the Fourier series near the boundary points. If you look at that in a function.
right, but it actually doesn't converge. I mean,
Right.
you bring in more series, it's still as bad.
It only shows up in the finite case, right? Well, for finite amount of terms, so there's some Gibbs phenomenon and if you go take that series all the way to infinity.
All right, well, let's leave that for, why don't we discuss that privately? I don't, offhand, I haven't thought about that. Let me give you a more dramatic example of the Gibbs overshoot. Although actually, this probably is more dramatic than the one I'm about to give you, but the one I'm about to give you is a little bit easier to estimate. So let's just take f of x equal x. And now again, let us take the interval from minus pi to pi. And we get the coefficients then b sub n is integral dx over pi x sine nx, and this is equal to 2 minus 1 to the n plus 1 over n. So that's the series. The a coefficients all vanish because the function is odd. And so we have here x is, I don't know why I didn't say x equals. But anyway, the series is n equals 1 to infinity, 2 minus 1 to the n plus 1 sine nx over n. And if we look at the picture, this is figure 2.4, the function going from, let us say, minus 2 pi. So this is really a square box, actually, but I drew it differently. The function x just does that. And this is 0, and this is 2 pi. What does the Fourier series do? Well, the Fourier series does the best it can from minus pi to pi, and so it's pretty good in here. It gets a little bit jittery, and then of course it has to do this. It has to drop by 2 pi and then start again because it's periodic. Well, again, it's jittery here, and then it's almost a straight line. And here it shoots up in a jittery way and then does that. So this is the series. In fact, I should use the colored chalk. So, in other words, that's the series, and that is, as I said, Gibbs overshoots of about 9% here. The actual function is this, and it's well represented from about minus 3 to 3, but we get an overshoot and an undershoot and so forth at the endpoints there. What you see actually from the figure is if you look at the second one where I just plot the overshoot, you see if I do 10 terms, a series with 10 terms has the dots, and with 10 terms the overshoots start earlier. And in fact, these overshoots are starting to get serious at 2, let alone 3. On the other hand, if you use 100 terms, then the overshoots don't start to get serious until 2.5. And so what happens is, as you use more and more, so this maybe is getting to what you were saying, as you use more and more terms, the function gets better and better, closer to the overshoot place. But you also can see here that where you have the overshoot, it's just about as bad with 100 terms as with 10 terms when you get actually to pi and minus pi. By the way, Gibbs's father was a lawyer, and he was not a lawyer, he was a linguist. And during the, let's see, when was this? This was back, I suppose, let us just say the time of the Civil War, maybe a little bit before the Civil War, but after the Civil War. It was a famous story, or true story, of the ship Amistad. And the slaves revolted, and there was a big fight, and the slave, the people running the slave enterprise were killed, and as the boat approached the U.S., the slaves would, or the Africans, I should say, I guess they were Africans, certainly African, they would call out and say, "Where are we? Is this the south or the north?" And at first they were in the south, and so they stayed away from the shore until they got up to Connecticut and came ashore. And then, of course, they were arrested and put on trial. Well, they couldn't speak English, and so it turned out that Gibbs's father, who was a linguist, did the translations in the trial. And I think they were acquitted in some way. I don't remember the movie or the story, but it's a very interesting and moving story. So it's one of the issues that if you look back to a period of slavery, which is what, 150 years ago, you realize that we talk a lot about religion, but do we mean it? And I was struck by, this point was made really well by Bernie Sanders at Liberty University yesterday. He did, or the day before, he gave a talk, and it was possibly one of the best political speeches since Franklin Roosevelt, I would say. You can, if you Google Sanders Liberty C-SPAN, you can get a nice video of the speech, and I'd recommend it. With all these churches, which we should tax, of course, with all these churches, I hope the dean doesn't ever watch this video.
He won't make it so far in the lecture.
All right, anyway, let's go on to stretched intervals. So far we've been talking about length 2 pi. And so let's go from 2 pi to L. How do we do that? Well, what we do is we use orthonormal functions on that interval, which are e to the I 2 pi n x over L. And we divide by square root L. Now, before it was square root of 2 pi, now it's square root of L. Notice how this has been constructed. When x is L, this is e to the 2 pi n. So it's the same as x equals 0. So this is periodic on 0 to L, on that interval. Periodic, well, it's periodic period, but the period is L, capital L. The orthogonality relation is 0 to L dx, e to the I 2 pi n x over L divided by square root of L star e to the I 2 pi mx over L square root of L equals delta nm. So this, it's clearly that's the right orthonormality integral, and that means that we can write the function f of x as a sum n equals minus infinity plus infinity f sub n e to the I 2 pi n x over L divided by square root of L. So this is a direct generalization of the original thing that I wrote at the start of the lecture. The fn's are integral 0 to L e to the minus I 2 pi n x over L square root of L f of x dx. And if the function f is periodic, then you can use any interval of length L, and it doesn't matter. The series is always going to be periodic with period L, no matter what the function is. And as I said, if the function is periodic, you can choose your interval arbitrarily. Okay. One can also write the function as a real, if the function is real. So if f equals f star, then we can say f of x is a0 over 2 plus sum n equals 1 to infinity an cosine 2 pi n x over L plus b sub n sine 2 pi n x over L. And you get a sub n is 2 over L integral 0 to L dx cosine 2 pi n x over L f of x. And b sub n is 2 over L 0 to L dx sine okay, so these are nice symmetrical formulas for the function. And then there are these orthogonality relations. I think I'll just leave them there, 241 to 243, without mentioning what they are. Okay, the next idea is functions in several variables. So far we've just been talking about x. We could be doing Fourier series for the floor of this room, in which case we'd have x and y. Or we could do for the volume of the room, we'd have x, y, and z. And we might as well just say that we have capital N dimensions, and then we would say f of x1, x2, dot, 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 x capital N would be then a sum n1 equals minus infinity to infinity, dot, 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 n sub capital N equals minus infinity to plus infinity, and this would be f n1 dot, 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 n sub n, and it would be e to the I pi over L. And I'm just going to use the dot notation, n dot x, with this vector meaning that we, in other words, n dot x is n1 x1 plus dot 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 plus n sub n x sub n. So it's that dot product. And on the other hand, f sub n1, n2, dot, 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 n sub n is integral minus L to L dx1, integral minus L to L dx sub n, e to the minus I pi over L n dot x. And now we have to divide by Okay, for some reason, here I had interval 0 to L. I've switched to interval minus L to L. So so the interval now is minus L to the L, and we divide by 2L to the N over 2. But I left out the 2L. I left out 2L to the N over 2 from that. And the reason why this works is that we have this orthogonality relation, namely the integral from minus L to L, dx1 dot 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 dxn of e to the, let us say, I pi over L n minus m dot x over 2L to the n is delta n1 m1 delta n sub n m sub n. So this is the orthonormality relation for these functions on, for some reason I didn't write down this relation in the book, but this is the orthogonality relation that generalizes this to n dimensions and an interval from minus L to L. And so this is the Fourier series then in n dimensions, and it works for arbitrary integer n. Okay, let's go to the front. I've run out of blackboard space, but that's just as well because the next topic is actually how Fourier series converge. And so what I'm going to do is I'm just going to read you some theorems that if we had an extra 2 weeks, we could prove these in detail. But I'll just quote them. Some of them are just definitions. First of all, a series of functions fn converges to f of x on a closed interval ab, what? If for every epsilon greater than 0 and every x less than or equal to b greater than or equal to a, that's what a closed interval is, there is an integer n depending on epsilon and x such that f of x minus f sub n of x is less than epsilon for all n greater than n of epsilon and x. So this is the lowest kind of convergence. This is what's called pointwise convergence. So at each point x, you have a special integer, and for each precision that you want, say 10 to the minus 6, and at each point, say a plus b over 2, there's some big integer such that if you're far enough out in the series, the error is less than 10 to the minus 6. So that's pointwise convergence. Well, we've run out of time, so I'll just start here next time. Are there any questions before we turn off the camera? All right. Remember, you get candy if you ask the question while class is in session. All right, let's quit.